Hey Math 206 students, welcome back. Last time we left off with this process I wrote down and it described how to diagonalize a matrix. So I want to just review that. I have it written up on the board and I want to go over it again. So here's the idea. We have an n by n matrix A and we want to go over the process for diagonalizing this matrix. So the first step is to find the eigenvalues, lambda 1 up through, and I'm writing here lambda 1 up through lambda k. Right? So A is an n by n matrix, but it may or may not have n eigenvalues. It might have some number less than that. So let's say it has lambda 1 up through lambda k. So there's step 1. Step 2, go through and find a basis for each eigenspace. So for each lambda I, there is the eigenspace E sub lambda I. Right? We need to find a basis for each one of those. Once we've done that, we take all the bases that we found in step 2, lump them together into a single set that I'm calling capital S, and I want to preserve the order. So the basis vectors for lambda 1 are going to go at the beginning, right? So when we write down the set capital S, write down the basis vectors P1, let's say up through P whatever, right? Put those in the first, then write down the, then add to that the basis vectors for E sub lambda 2, then E sub lambda 3, all the way down the line until we get to the basis vectors for E sub lambda k. Put all of those together in a set capital S. Now, if S has fewer than n vectors, we're done. A is not diagonalizable. If, on the other hand, S has n vectors, right? So where n matches the dimensions of the matrix A. Then we have, so we've got S written out as P1 up through Pn. Then we know that our matrix A is diagonalizable, right? It is similar to this diagonal matrix, capital D, where along the diagonal we put the eigenvalues. Now, notice here I've written it as lambda 1 through lambda n, right? D is going to be an n by n matrix. If, for example, E sub lambda 1 had dimension 3, so that there are 3 basis vectors for the first eigenspace E sub lambda 1, then what I would do is I would put lambda 1 3 times along the diagonal, right? So corresponding to the dimension of the eigenspace will be exactly the number of times that lambda appears on that diagonal. We'll see this in some examples, but the point is when we write down D, it's going to be an n by n matrix. Even if we only had k eigenvalues, right? D is going to be dimension n. So anyways, we'll see this when we do some examples. Also then, the matrix P is going to be the matrix whose columns are in order P1 up through Pn, the basis for the eigenspaces. Okay, so let's see this process in action now. So as a first example now, let's look at this matrix. We've already seen this matrix. So let's see, A is going to be the matrix 5, 8, 16. And then 4, 1, 8. And -4, -4, 11. This matrix, we already computed the characteristic polynomial. So the characteristic polynomial is lambda minus 1 times lambda plus 3 quantity squared. We found bases, so the basis for E1 consists of a single vector, and it's -2, -1, 1. -2, -1, 1. And the basis for E sub minus 3, that one consists of 2 vectors, and so it's going to be -1, 1, 0, and -2, 0, 1. Okay. So now the process that we described a minute ago, here we've got a 3 by 3. And when we lump our vectors together, we're going to have 3 eigenvectors. So our set capital S consists of the 3 eigenvectors, -2, -1, 1, -1, 1, 0. and negative 2, 0, 1. So our theorem from last time said that a matrix is diagonalizable if and only if Rn, in our case R3, has a basis consisting of eigenvectors for our matrix A. Because we had 1 for E1 and 2 for E negative 3, right? Here we have a basis of eigenvectors for R3. So our conclusion then, our matrix A is diagonalizable. D equals P inverse A P, where D is going to be the matrix. So what do I have? I have my first eigenvector in my basis corresponds to 1. So on the diagonal, in that first position, I'm going to put a 1. Now, the next two eigenvectors correspond to E sub negative 3. And so along the diagonal, in the second two positions, I'm going to put negative 3. So the eigenvalue negative 3 appears twice in order corresponding to the two basis vectors that belong to the eigenspace E sub minus 3. And then P is, of course, the matrix whose columns are the ones that you see there. So it'll be a negative 2, negative 1, 1, minus 1, 1, 0, negative 2, 0, 1. There it is. Okay, so let's try. Oh, actually, before I do an example, here's one thing I want to notice. In our case, in this example right here, we had two eigenvalues, two distinct eigenvalues, for a matrix that was a 3 by 3. So in that case, we had to go through and we had to count basis vectors and make sure that we had actually a sum total of 3 basis vectors before we knew whether our matrix was diagonalizable or not. If there's a situation where the matrix has, if it's an n by n matrix and it has n distinct eigenvalues, then you're guaranteed that it's diagonalizable because you're going to have at least one basis vector always for an eigenspace. And so if you have n distinct eigenvalues, you're guaranteed that your matrix is diagonalizable. So I'm going to write that down. So we'll say corollary. If the n by n matrix capital A has n distinct eigenvalues, then A is diagonalizable. Okay, before we go on to some examples, what we want to do is get some terminology down that corresponds to the number of times that an eigenvalue and an eigenvector appear. So let's say, suppose the n by n matrix A has characteristic polynomial, and I'm going to write it out in factored form. So it's going to look like this, say a sub 1 minus lambda 1 raised to the m1 times a sub 2 minus lambda sub 2 raised to the m2, all the way down to, let's say, a sub k minus lambda sub k raised to the m sub k. All right, so here's our characteristic polynomial. We have k distinct eigenvalues. Now, there's two definitions here. So the algebraic multiplicity of the eigenvalues, say lambda I equal to, so notice, for example, the first eigenvalue is a sub 1, right? Because a sub 1 is a root of this polynomial. Second eigenvalue is a sub 2, and so on. So of lambda I equal to a sub I is, and we write it ALG of a sub I equals the power that you see appearing in the polynomial. So algebraic multiplicity of a sub I is equal to m sub I. Right, so there's the algebraic multiplicity. There's also what's called the geometric multiplicity. So the geometric multiplicity of lambda sub I equal to a sub I, so of the ith eigenvalue, the geometric multiplicity is, and we write that as GEOM of a sub I, and that's equal to the dimension of the corresponding eigenspace. So it's the dimension of E sub lambda I. So for each eigenvalue, there are two numbers associated, the algebraic multiplicity and the geometric multiplicity. And here's a true fact. We'll say it over here. So fact, the geometric multiplicity of lambda sub I is always less than or equal to the algebraic, or I guess I'm using a sub I. So geometric multiplicity of a sub I is always less than or equal to the algebraic multiplicity of that same eigenvalue. Right? So geometric multiplicity is always less than or equal to the algebraic multiplicity. Now, what do we know? We know that a matrix is diagonalizable if and only if there's a basis consisting of eigenvectors. Now, if we take all the algebraic multiplicities and add them together, m1 plus m2 plus blah, 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 all the way to m sub k, that's going to add up to the degree of this polynomial right here, which will be exactly equal to the number n. Right, the number n. The algebraic multiplicities then match, right, the sum of the algebraic multiplicities match the degree of the polynomial. The geometric multiplicities could be smaller though. Now, when is a matrix diagonalizable? Well, it's if and only if we have a basis of eigenvectors. When is that going to occur? Exactly when the dimensions of the eigenspaces add up to the number n as well. So this gives us a nice way, I don't say quick, but a nice way to think about or to characterize when a matrix is diagonalizable. It's going to be diagonalizable if and only if the algebraic multiplicities equal the geometric multiplicities for all of the eigenvalues. So let's say it like this. We can call this a corollary. So a corollary. Yeah, so A is diagonalizable if and only if the geometric multiplicity of lambda equals the algebraic multiplicity of lambda for every eigenvalue lambda of A. So, and this is really the way, when I'm working with diagonalizability, this is the way I think about it, or the way I remember it, is I remember that geometric multiplicities have to equal algebraic multiplicities all the way down the line in order for a matrix to be diagonalizable. Okay, so now let's look at some more examples. So here's the instructions. Determine whether A is diagonalizable by comparing algebraic multiplicity of lambda and geometric multiplicity of lambda for each eigenvalue lambda. If diagonalizable, find P and D so that D is equal to P inverse A times P. All right, so I think I'm going to do two examples. And the instructions will be exactly the same for both of them. So first example, my matrix A is going to be a 4 by 4 matrix. And I'll tell you row by row, so 1, 0, 0, 4. And then 0, negative 1, 1, 8. 0, 8. Negative 8, 5, 16. And 0, 0, 0, 3. 0, 0, 0, 3. All right, so there's our matrix. If we compute the characteristic polynomial, and I won't make you go through all this process, it actually factors pretty nicely. The characteristic polynomial, in fact, this example is rigged to make sure that the characteristic polynomial works out nicely. It's 1 minus lambda squared times 3 minus lambda squared. All right, so it factors nicely. And what we can see here is that there are exactly two eigenvalues, right? Lambda equals 1 and lambda equals 3. So the algebraic multiplicity of 1 is equal to 2, and the algebraic multiplicity of 3 is also equal to 2, right? The algebraic multiplicity is the exponent that you see when you have the characteristic polynomial in factored form. Okay, so now what we're supposed to do is we want to compare algebraic to geometric multiplicity and see what happens to decide whether it's diagonalizable or not. And so let's first look at the geometric multiplicity of the eigenvalue lambda equals 1. So I need to find the dimension of the eigenspace E sub 1. All right, so what do? I'm going to subtract 1 from each diagonal entry. 0, 0, 0, 4. And remember, I'm looking at the null space of A minus lambda I. So I'm subtracting, and so that's why I'm going to put zeros over here. We're looking at the homogeneous system. 0, minus 2, 1, 8, 0. 0, minus 8, 4, 16, 0. 0, 0, 0, 2, 0. Okay, so here's the system that we want to solve, right? Our matrix is to the left of that line right there after subtracting 1 from each diagonal entry. All right, let me set that equal to the 0 vector and solve. All right, so I'm trying to find a basis for the null space. Now, I won't make you go through all the steps. When it's all said and done, right, when you do the row operations, here's where we end up. It's going to be 0, 1, negative 1 half, 0. 0, 1, negative 1, negative 1 half, 0, 0. Then 0, 0, 0, 1. 0, 0, 0, 1, 0. And then we have 2 rows of zeros. All right, so what that tells us is we have 2 free variables. That tells us the dimension of the null space, right? Which means that the geometric multiplicity is equal to 2. Right? So from this right here, we can see that the geometric multiplicity of 1 is equal to 2. So we get a match here. And while we're at it, we might as well write down who the basis is going to be. So let's see, let's call x2 equal to, x1 is free. So x1 equals s, and who else is free? x3 is free, so x3, let's call that t. So then x2 is equal to 1/2 t. And who else? x4 is, x4 has to be 0. So the general solution looks like this. S 1/2 t, t, and 0. Make sure I got that. Yeah. Which we can split up as, so that would be S 0, 0, 0 plus t times 0, 1/2, 1, 0. So for our basis, I don't really want to have fractions, so I'm going to choose, I could have factored a 1/2 t out of there. So as a basis, okay, never mind. I'm going to leave it just as it is. So my basis, oh, I should have erased that. 0, 0, 4, 4. Okay, so my basis, oh, and I didn't factor, sorry, this should have been an S there and a 1 there. So my basis, sorry, I just don't have enough room here. My basis is 1, 0, 0, 0, and 0, 1/2, 1, 0. Okay, so there's the basis for the eigenspace E sub 1. Now I need to move on to E sub 3. Okay, so now I need to subtract 3 from each diagonal entry. So we'll get -2, 0, 0, 4, 0. 0, -3, 1, 8, 0. 0 minus 8, 2, 16, 0. And 0, 0, 0, 0, 0. I'm going to leave that up if I can. So, what's next? Yeah. So if you do the row operations, and I did this one, so it comes out like this: 1, 0, 0 minus 2, 1, 0, 0 minus 2, 0, 0, 1, -1/4, 0, 1, -1/4, 2, 0, 0, 0, oh, and then 2 rows of 0. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so once again, we have 2 free variables, right? These ones are free, so this tells us that the geometric multiplicity of 3 is also equal to 2. So now we have algebraic multiplicities match geometric multiplicities for both eigenvalues. That means that the matrix is diagonalizable. So in this case, x3 is free, so let's call that S. x4 is free, so let's call that one T. And now the general solution, oh wait, x1 is 2T, and x2 is 1/4 S minus 2T. So the general solution looks like 2T 1/4 S minus 2T ST which will be S times 0 1/4 1 0 plus T times 2 negative 2 0 1. Yeah. Okay. So now we can see the basis vectors for E sub 3 also. Now one thing, and I kind of hesitated a minute ago, it's nice to have a matrix that doesn't have fractions. So one thing to notice, if you have a basis vector, then any multiple of that, any non-zero multiple, is also a basis vector. So to clear out the fractions, if you want, you can multiply this basis vector by 2. And so another basis for E sub 1 is 1 0 0 0 and 0 1 2 0. You don't have to do this, but if you're checking your answers in the back of the book, they're usually going to clear out the fractions if they can. So here's a basis for the first one. And for the second one, so for E sub 3, our basis consists of, I'm going to multiply this first basis vector by 4 to clear out the fractions. 0, 1, 4, 0, and 2 minus 2, 0, 1. You don't have to do this. You could leave the basis just as you see it right here. I won't, on an exam, I'm not going to mark it off. But if you're checking your answers, it makes it easier to see what's going on. So the matrix is diagonalizable. And so what we have is that D is equal to P inverse A times P, where D is going to be the diagonal matrix where, in order, the diagonal entries, we've got 1 appearing twice and 3 appearing twice, corresponding to their algebraic multiplicities. And then P is the matrix. Now I need to get things in order. I need the eigenvectors corresponding to 1 to come first. So those are going to be 1, 0, 0, 0, 0, 1, 2, 0. Then the eigenvectors corresponding to 3 make up the second 2 columns. Doesn't matter what order I do. 0, 1, 4, 0, 2 minus 2, 0, 1. So that's it. And by the way, if I would have listed these 3's first, then I would just put those 2 columns first also. So it doesn't matter, as long as you're consistent. Make sure that the columns of the P matrix correspond to the entries on the diagonal matrix. Okay, so let's do another example. Or I'm just going to the same instructions, but we're going to have a different matrix. So A is going to be the 3 by 3 matrix. Minus 1, minus 3, minus 9, 0, 5, 18, and 0, minus 2, minus 7. 0, minus 2, minus 7. I know these matrices look weird. They're cooked up, right, to get nice characteristic polynomials. So it turns out the characteristic polynomial in factored form is negative times quantity 1 plus lambda cubed, which means that we have exactly one eigenvalue, right? Just lambda equals negative 1. And so what we have is algebraic multiplicity of our only eigenvalue is 3, right? It's the exponent. So the algebraic multiplicity of negative 1 equals 3. Now we need to compute the geometric multiplicity by looking at the dimension of the eigenspace. So that means that I'm going to take the matrix A and subtract negative 1 from each of the diagonal entries, which means I'm going to add 1. So we're going to get a 0, negative 3, negative 9, 0. 0, 6, 18, 0. 0, minus 2, minus 9, minus 8, 0. Now, if you do the row operations, here's what you'll end up with. So if you do the row operations, here's what we get. So it's going to be 0, 1, 3, 0, 1, 3, 0. And then everything else is zeros. So what does that tell us then? We have one leading one. So that means that there's two free variables. Right there, x1 and x2. So what does that tell us then? The geometric multiplicity of negative 1 is equal to 2. So algebraic multiplicity does not match geometric multiplicity. That tells us that A is not diagonalizable. So we'll say it like this: since the algebraic multiplicity of minus 1 is not equal to the geometric multiplicity of minus 1, capital A is not diagonalizable. Now, I want to talk a little bit more about diagonalizability, but really I want to talk about now why. Who cares, right? Why would you want to diagonalize a matrix? And I discussed this a little bit earlier, that diagonal matrices are much easier to deal with, right? Multiplying diagonal matrices, easy. Raising them to powers, easy, right? Seeing how they behave on Rn, also easy, because you can see what it does to each eigenspace. It just scales the vectors in that eigenspace. So as one application, so let's say application. Let's say raising, I don't know how I want to say this, raising matrices to powers. So what I want to do as an example here, so let's compute A raised to the 1000, where A is the matrix negative 9, 4, negative 20, 9. Now, can you imagine if you started multiplying this matrix out? It'd be a nightmare. Right? I mean, you got to do this 1,000 times. This matrix times itself 1,000 times. Right? That would take forever. It'd be a lot of work. So here's the idea. It turns out that this matrix is diagonalizable. Right? So it turns out, and you can go through the steps here. So it turns out that D is equal to P inverse A P where, let's see, or D, so you can go through and find the eigenspaces and compute the matrix D. So there are two eigenvalues, 1 and -1. So D equals 1, 0, 0, -1. And P equals P equals 2152. 2152. So now A is equal to P D P inverse. So A to the 1000, here's the point. A to the 1000 is going to be equal to this matrix raised to the 1000. So P D P inverse raised to the 1000. I mean, in a way, it looks worse for the moment. But that's equal to P D P inverse times P D P inverse. Blah, 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 blah. Keep it going. P D P inverse. There's 1,000 of these written down. And notice what happens inside. The P inverse cancels with the P. Right next to here, there will be a P, so all the P's in the middle cancel. The D's are left together, so this is equal to P D to the 1000 times P inverse. So let's see now. If I take D to the 1000, what's going to happen? Well, when you raise a diagonal matrix to any power, all that amounts to is raising each of the individual entries on the diagonal to the 1000th power. So 1 to the 1000th is 1. Minus 1 to the 1000 is also 1. So this is equal to P times the identity matrix times P inverse, which in this case is equal to the identity matrix. Totally not obvious that if you start multiplying this matrix 1,000 times, when I just look at it, it looks terrible. Right? Raise that to the 1000th power, comes out to the identity matrix. Now, you might say, okay, why? Why would you ever want to do this? I have a story to tell. I think this was the very first time I taught linear algebra. I had a student, and he was working on video games, right? Trying to make video games, and especially the graphics. So what he had was, I think he had a helicopter, and he just wanted to make the helicopter he'd fly across the screen. Right? So the helicopter is going to move. Now, how you do that, there's a matrix that tells the different pixels of the helicopter where to go as time elapses. Right? So what you want to do is then you have a matrix that says be here, be here, be here, be here, and it amounted to, so there was a matrix A, and as time elapses, after 1 second, or at time 1 second, the helicopter is at position A to the first. It's actually more than 2 seconds. It was actually much faster. Let's say so 2 1/millionths of a second or something like that. Anyways, the process of making the helicopter go across the board amounted to raising a matrix to higher and higher powers. Right? So as time elapsed, you had it raised to higher and higher powers. And here's what was happening. He was finding that as he ran it, it would run smoothly, smoothly, and it would start to glitch and glitch, 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 glitch until it would basically hang up. What was the reason? It was because he was telling the computer to do computations like this. If you raise A to the 1000th power, I think he actually had to raise it to even higher powers like that. It is a very, very slow process. And so he brought this problem to me, and towards the end of the semester, and said, here's the situation. I'm trying to make this helicopter go across the screen, and it's hanging up. And once he described what was going on, I realized, oh, what's happening here is that you're trying to raise a matrix, tell a computer to multiply a matrix a whole bunch of times. That is a very, very slow process. My immediate question to him is this matrix diagonalizable? And so he said, I don't know. He went back and checked and found out that it was. It was a diagonalizable matrix. And so what he did then is he expressed his matrix in this form right there. Got this? So A to the, let's say A to the n was equal to P d to the n P inverse. Computing d to the n is super quick. So instead of having to do 1,000 or whatever n matrix multiplications, there's only 2 operations. P times d to the n times P inverse. Once he diagonalized the matrix and rewrote the code to do it in this form right here, the helicopter smoothly flew across the screen. Right? So there's a reason why you might want to diagonalize a matrix. Okay, see you next time.